All right, guys, mathematically a sequence. So this is a function whose domain is the set of all positive integers, right? So here's, and you have a mapping of those natural numbers onto the terms of the sequence. So for example, let's look at this first one. We have an explicit formula given here. A sub n equals 3 plus negative 1 to the n. So if we let n be 1 first, then we're finding a sub 1. So we would have 3 plus negative 1 to the 1. And that's our first term. So 3 minus 1, we got 2. That's our first term, or a subscript 1. Now if we let n be 2, all right, so we're finding a subscript 2. 3 plus negative 1 squared is what we're doing. N is now 2. So we got 3 plus positive 1. So we got 4. That's our second term. Now if we let n be 3 in the formula, right, in this, we're plugging it into this every time. If I let n be 3, so I'm finding my third term. My third term would be a sub 3, 3 plus negative 1 to the third. Well, negative 1 to the third is negative 1. So it spits out 3 plus negative 1 spits out 2. So our third term is 2. Our fourth term would be and so on, right? So this sequence is 2, 4, 2, 4, and so on, right? This next one, b sub n equals n over b sub n. Here's your explicit formula, n over 1 minus 2n. This is a good one. Go ahead and write out all the terms, or the first 4 terms or so. Good time to pause the video. Well, here's our first term, 1 over negative 1. So negative 1 is our first term. Now let's find our second term. 2 over negative 3, so negative 2 thirds. Let's find our third term. 3 over negative 5, so negative 3 fifths is our third term. And so on. So our first term is negative 1, second term is negative 2 thirds, third term is negative 3 fifths, the next one would be that negative 4 sevenths, and so on. And there's the sequence. Let's do this next one. Let's find the first term. So we'd have 1 squared over 2 to the 1 minus 1, so I have 1 over 1. Now let's find the second term. So I'd have a 2 as my n. So 4 over 3 is my second term. Third term, I have 9 over 2 to the third minus 8, 9 over 7, and so on. So if I was writing this sequence out, first term's 1, second term's 4 thirds, then I got 9 sevenths. By the way, the next one would be 16 fifteenths, and so on. Those are some terms. This next one is what's called a recursively defined sequence. So instead of having an explicit formula where I can go directly to, like if I wanted to go with the C subscript, if I wanted to go directly to the 10th term, I could find the 10th term, right? That's called an explicit formula for a sequence. This one is recursively defined. So let's look at it here. I have d subscript n plus 1. So the next term is the prior term minus 5. So see how they give us d1, the first term? They give us d1, right? So if I'm trying to find the second term, what would I have to let n be? Yeah, let n be 1. So that would give me the second term. So the second term, let me come over here, the second term is the first term minus 5. Well, the first term they gave us is 25. So the second term is 20. Again, that's recursively defined. Now I'm going to let n be 2. So I'd have d2 plus 1 equals d2 minus 5. So the third term is the second term minus 5. So the third term is, what was our second term? Looks like it was 20. So the third term is 15, and so on. And then I would write all of those numbers as my sequence, right? So it'd be 25, then it's 20, then it's 15. Of course, the next one would be 10, and so on, right? And that's my sequence d sub n. All right, there's also a couple different ways to represent sequences graphically. The first one here is just based on, this is like if it was square root of n. So like square root of 1 is right there at 1. Square root of 2 is like 1.4-ish, right? Square root of 3, 1.7-ish. Square root of 4, of course, is 2, right? And then square root of 5 is 2 point something, whatever that is. Anyways, you could graph them on a number line, right? And you could show them, label them A1, A2, A3, A4. Two-dimensionally, if you were doing it two-dimensionally and you were graphing a sub n equals the square root of n, the horizontal axis is still your input, and your output is what you get for the value of that term, right? So if n is 1, the square root of 1 is 1, right? So it'd be n, a subscript n is what you're graphing. So if n is 1, the square root of 1 is 1. If n is 2, the square root of 2 is the output, and you graph that point. If n is 3, you graph whatever the square root of 3 is. N is 4, square root of 4 is 2, right? And you have that point 4, comma 2 right there, and so on. All right, so you have the two different ways to graph sequences. And then there's two, I would call them just special types of sequences. Arithmetic and geometric are some special ones. And so they have some formulas involved. Let's see if we can recognize this first one here. See how you have 3, 7, here, let me write this. 3, 7, 11, 15, 19. What's happening each time? To get the next term, what do? Good, you're adding 4. See how you added 4, and then you took the 7 and you added 4, and you added 4, right? Oops, add 4, not 5. 4. Okay, this is called an arithmetic sequence, and that is called your common difference. So you have a common difference of positive 4. It's called the common difference. Okay. And then for an arithmetic sequence, again, I'm doing an arithmetic sequence. So it either adds something each time or it subtracts something. If I was subtracting something, my d would be a negative value. Okay. But in this case, I'm adding 4 every time. This is the explicit formula for an arithmetic sequence. So if we were coming up with this formula, I would say, well, a sub n is the first term plus n minus 1 d. So the nth term is the first term. Our first term is 3. So that's our first term. 3 plus n minus 1 times our common difference. And then I would just clean that up. So an equals, let me distribute that, 4n minus 4. So I have 3 plus 4n minus 4. So 4n minus 1. And that'll give me any term I want. So for example, if I'm trying to find the 5th term, I know the 5th term is 19, right? But let's check it. The 5th term is 4 times 5, n is 5 minus 1. 20 minus 1, 19. The 5th term is 19. I can go directly, now I have an explicit formula, because it's an arithmetic sequence, I can go directly to any term that I want. We can also write arithmetic sequences as a recursive formula too. So the next term is the first term plus the commas, is the prior term plus the common difference, right? But what's the power of the explicit formula? Well, I can go directly to, like, let's say the 105th term. Whereas with a recursive formula, if I'm going to get the 105th term, so I'd let n be 104, then I need to know the 104th term, right? That's the problem with the recursive formula. So, all right, now let's go to geometric sequences. Geometric sequences, these have what's called a common ratio. They have a common ratio. So you're multiplying by something each time. So if you look at 2, what do you multiply 2 by to get negative 2/3? And then what do you multiply negative 2/3 by to get 2/9? What do you multiply positive 2/9 by to get negative 227? And so on. What is the common ratio? What are you multiplying by each time? Negative 1/3. That's right. You're multiplying by negative 1/3 every time. Multiplying by negative. So our common ratio is negative 1/3. Now, if you're not sure, the way to find a common ratio, if you suspect you have a geometric sequence, meaning I'm multiplying by some every time. If you suspect you have a geometric sequence, you can check it. You can get the common ratio by taking the second term divided by the first term. So negative 2/3 over 2, that'll give you negative 1/3. And it better be the same thing as the third over the second. So 2/9 divided by negative 2/3, guess what? Gives you negative 1/3. It better be the same every time. So the fourth over the third will give you negative 1/3. The fifth over the fourth will give you negative 1/3. That's how you find a common ratio, but it's got to be the same, right? It always has to be the same R. Now that you know your common ratio, the explicit formula for a geometric sequence is a sub n is a1 r to the n minus 1. So in this case, the nth term is the first term, there's our first term, 2, times the common ratio, which we know we're multiplying by negative 1/3 each time, to the n minus 1. And that'll spit out any term that we want. You can write that in a different form if you really wanted to. You could write that as 2 times negative 1/3 to the n times negative 1/3 to the negative 1, right? That's the same thing. Or negative 1/3 to the negative 1's 3 over 1 to the 1. 2 times 3 is 6. So this is also the same thing. 6 times negative 1/3 to the n is the same thing. If you want to go to that effort, move up a little more, right? All right, so the limit of a sequence graphically, and this is taking us back to the formal definition for all epsilon greater than 0, there exists an n greater than 0, blah, 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 right? The formal definition of a limit. Graphically, this is saying if your sequence has a limit, then it will converge to that limit L, capital L, that's within the band, right? Can you see how here's your L plus epsilon, L minus epsilon? Here's a first few terms might be over here, but eventually it's getting within the band, and it's going to approach that limit, right? If it has a limit, right? And so you're shooting this out. Does it have a limit? Well, as I let n increase in magnitude to infinity, if it approaches L, then yeah, the sequence converges to L. If it doesn't, if it's not bounded, right, then I don't. It diverges. So this theorem down here is saying, with sequences, like we're letting n be 1 and 2 and 3 and 4. But you can think of it, if a sequence agrees with a function at every positive integer, and if the function approaches the limit as x goes to infinity, then the sequence must also converge. So we can think about this as all real numbers too, right? So if the sequence has a limit, think of it in terms of the function. But we're going to just keep it in terms of n. Okay. All right, let's go ahead and look at this first one. And let's see if we can find the limit on this. Find the limit of the sequence whose nth term is. And a solution on this, remember, it's been probably a little bit, but remember from pre-calculus, that the limit as x goes to infinity of 1 plus 1 over x to the x is the definition of the irrational number e. That's right. Therefore, the limit as n goes to infinity, again, n is talking about all our natural numbers here, right? So if the limit as x goes to infinity for all real numbers ends up being e, then for the sequence, as n gets increasingly large, 1, 2, 3, 4 to infinity, would also be e. Okay, and that's showing that theorem that we just had on the last one. Okay. Well, there's different ways in which a sequence can fail to have a limit, right? You can have it increase without bound, right? So this would diverge. It just keeps getting larger and larger. So for example, 1, 2, 3, ... right? It just keeps getting bigger, 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 right? That's a diverging sequence. This next one too, if you shoot to negative infinity, like 0, -1, -2, ... right? Just keep shooting down. This also diverges. Right? We don't converge to a value. It's not bounded at all. There's other ways in which a sequence can fail to have a limit. Like this one, 1, -1, see right here, 1, -1, and so on, blah, blah, blah. And you see how it just keeps bouncing back and forth between 1 and -1. And so you're just oscillating. So that's divergent, right? You're not converging to anything. This one's not only changing from negative to positive, right, but it's bouncing back and forth from 1 and then down to -2 and then up to 3 and down to -4, right? So it's bouncing up and down, as well as the absolute value is increasing in magnitude. So all these, again, are all divergent, right? They're not bounded at all. So if you disregard the initial set of, the convergence or divergence of a sequence not affected by the initial values. However many of those initial values you want that to be, like maybe it's only 5 or 6, but eventually this thing is bounded, right? It gets closer and closer and closer to that L. So for a convergent sequence or divergence, it's not affected by the initial number of terms. That number of terms might be 5, might be 10, might be 100, right? But the question is, does it eventually settle down and is bounded? That's the question of whether a sequence has a limit. And here's some properties of limits of sequences. These are the old properties you had in your calculus 1. All right, let's look and determine the convergence or divergence. We had this one earlier when we were introducing them, right? And it was 2, 4, 2, 4. Does this converge to a number? Good, it does not. So it alternates, right? Or oscillates. Alternates. So therefore, the limit as n goes to infinity of the sequence does not exist. And sequence diverges. In other words, sequence is divergent. This one we had n over 1 minus 2 to the n. And so if we just, and you could list it, and you might be able to see it, but we're going to go ahead and let's test it. You could do this a couple different ways. L'Hopital's rule works, but let's go ahead and practice our algebra, where we take the largest value degree of the denominator, we divide everybody by that. So see that n on the bottom, negative 2n? So divide everybody by n, top and bottom. In other words, you're multiplying the top by 1 over n, and you're multiplying the bottom by 1 over n. And so what you have is the limit as n goes to infinity of 1 over n minus 2. And again, we did this because it was infinity over infinity, right? Initially, it was indeterminate in form, so we had to manipulate it algebraically, or we could have used L'Hopital's, right? But I wanted to just practice an algebraic technique. Now let's let n run to infinity and see if we have any issues. Well, the limit as n goes to infinity of 1 over n, so 1 over a huge number goes to 0, right? And so we've got 1 over 0 minus 2, so I got negative a half. And so, yeah, this limit as n increases in magnitude, our limit is negative a half. It gets closer and closer and closer to negative a half. Therefore, sequence converges to negative a half. The sequence converges to negative a half. Let's look at this one. Determine convergence on this one. Limit as n goes to infinity of n squared over 2 to the n minus 1. Well, notice we have infinity squared over 2 to the infinity minus 1. We've got infinity over infinity. Now, there's no algebraic technique for this. We're going to be forced to use L'Hopital's rule. So this is the same as the limit as n goes to infinity of derivative of n squared is 2n. Derivative of 2 to the n is ln of 2 to the n, and then minus 0, right? Derivative of constant 0. Well, notice if I let n go to infinity, see how we have infinity over infinity again? So let's go ahead and repeat it again. Good old L'Hopital's rule again. Derivative of 2n is 2. The ln of 2 stays there. Now I take the derivative of that 2 to the n as another ln of 2 to the n. All right, so we've got the limit as n goes to infinity of 2 over ln of 2 squared 2 to the n. Now let's investigate as n goes to infinity and see how we got 2 to the infinity. So on the bottom is getting huge, right? So this is going to 0. I got 2 over a huge, huge number, right? So this is going to 0. Therefore, we can conclude the sequence converges. Sure enough, it does converge to 0. L'Hopital's rule helped us to get there. Why don't you guys try this one now with L'Hopital's rule? See if this thing converges or diverges. Well, as you did this, hopefully when you investigated, whoops, I wasn't supposed to put the answer there. Sorry about that. You have infinity over infinity, so you got to use L'Hopital's rule. So you have the limit as n goes to infinity, derivative of the natural logs, 1 over n, derivative of n is 1. So we've just got the limit as n goes to infinity of 1 over n. So as n goes to infinity, I got 1 over this huge number, so that goes to 0, right? So yeah, this sequence does converge. And it also converges to 0 again. Okay. So yeah, we're treating n as a continuous real variable and differentiating with respect to n instead of rewriting everything in terms of x, right? And then we're using that theorem. All right, let's talk about n factorial. N factorial. So 0 factorial is a special case. That's 1. 1 factorial is 1. 2 factorial means 2 times 1. 3 factorial means 3 times 2 times 1. 4 factorial means 4 times 3 times 2 times 1, and so on, right? And algebraically, you know, if you're working with these, like a 2n factorial would be different than like 2n factorial, right? You have n factorial, and so on. So anyways, that's your factorials. Let's do some problems with some factorials. This first one here is introducing a squeeze theorem. You may remember that from pre-calculus. It's also referred to as the sandwich theorem. And the squeeze theorem will help us to determine, sometimes you can squeeze a sequence and determine if it has a limit that way. So here's an example of that. Let's go ahead and write out some of these terms here. C sub n, here's the formula I'm using. So the first term would be negative 1 to the 1 over 1 factorial. So I got negative 1 over 1 factorial, so I got negative 1. There's my first term. My second term would be negative 1 squared times 1 over 2 factorial. So I got negative 1 squared is just a 1. 2 factorial is 2 times 1. So the second term is 1/2. The third term, negative 1 to the third, is 1 over 3 factorial. So I've got negative 1, 3 times 2 times 1 is 6. So I got negative 1, 6. Okay, so let's list this. Negative 1, and I get a half, then I get a negative 6. The next one would be 1/24, and so on. Right? Here's the sequence, just to get a feel for it. Now I kind of gave away a little bit on this to kind of exemplify the squeeze theorem. What it is squeezed by, in other words, a lower bound and upper bound. So to apply the squeeze theorem, consider an being negative 1 over 2 to the n, right? And so your first few terms would be negative a half if I let n be 1, if I let n be 2, negative a fourth, negative an eighth, negative a 16th, and so on, right? And this will bound it below as soon as you hit anything for n being greater than or equal to 4. This is bound. So see how as soon as you hit the fourth term, you're bounded below for any term, fourth term and above. Okay. Now we'll also consider where we'll call it the bnth as the positive 1 over 2 to the n. All right. So this would be 1/2, 1/4, 1/8, 1/16, da da da. And this is bounding it above. And so we know again, after the fourth term, this is squeezed in there, right? If you can see it in the graph. It's squeezed between the 1 over 2 to the n is the above and negative 1 over 2 to the n from below. It's bounded between those two. So let's start making some conclusions here. So since the limit as n goes to infinity of the bounded above, the a sub n, so the limit as n goes to infinity, I'm sorry, that's my below one. That's my below one, negative a to n. As we run this to infinity, this is a huge number on the bottom, so this goes to 0, right? So that's the bounded below, that limit. Now let's look at the bounded above. the b sub n, does it converge? Yeah, that also goes to 0, right? So the sequence between them, which was our original sequence, so we have it's between the two. Therefore, right, since this is converging to 0 and that's converging to 0, then the sequence between them, despite the initial few terms, the sequence between them must also converge to 0 by the squeeze theorem. These are just some additional examples of the squeeze theorem in action here. Cosine of n is squeezed between 1 over n and negative 1 over n, and both of those go to 0. So we can conclude that that also converges to 0. 1 over 2 to the n squeezed between those two, which both go to 0. So we can conclude it also goes to 0, and so on. So those are just a few more. All right, let's look and see now. Sometimes you're just given a sequence and you're not given the explicit formula, and you're just expected to come up with, hey, can you discover the pattern, right? And then we can then investigate convergence or divergence of the sequence, right? But it's nicer, obviously, if you have that formula in order to investigate that. So if you're looking at this first one, 2, 8, 14, 20, hopefully you notice that this is doing what? Good. Going up by, up by 6. Can you see how that's going up by 6 every time? So this is an arithmetic sequence. That's called a common difference. Number one, notice it's adding 6 each time. Again, if you're adding a certain amount or subtracting a certain amount every time, that's an arithmetic sequence. So common difference is positive 6. This is an arithmetic sequence. And with an arithmetic sequence, you want to make sure you have this written down. The explicit formula, a sub n, is the first term plus n minus 1 times that common difference. So now we can come up with the formula for the nth term. So the nth term would be the first term. First term is 2. N minus 1 times our common difference is 6. So the a sub n is 2 plus 6n minus 6, or 6n minus 4. And notice that'll give us any term that we want for this. All right, let's try this one now. Oops. Well, we actually did this one earlier, this exact sequence. Can you see how it's being multiplied by 1/3? Oh, I think the other one was actually negative 1/3. It's multiplying by 1/3 each time. That's 1/3, right? So we have a common ratio. So this is a geometric sequence. And if you're not sure, to find the common ratio, you take the second term over the first term. So negative 2/3 over 2. And you see how that's, oops, negative 2/3 over negative 2. Sorry about that. Which gives you the 1/3, right? And that should be the same thing as the third term over the second term. So negative 2/9 divided by negative 2/3 is also 1/3. And that should be the same thing as the fourth over the third would also give you 1/3. So you definitely have a common ratio here. You are multiplying by 1/3 each time. So it is a geometric sequence. So note this is geometric. I'm multiplying by something each time with a common ratio of 1/3. the formula for a geometric sequence is a sub n equals a1, the first term, times a common ratio r to the n minus 1. So a sub n equals the first term, which is -2, times the common ratio, which was 1/3, to the n minus 1. And that'll spit out any term you want. You could clean that up if you wanted to a little bit. That's the same as 1/3 to the n, 1/3 to the -1. So that's 3/1 to the 1, or -6 times 1/3 to the n. Either of those are fine for the explicit formula. Let's find a sequence whose first 5 terms. Can you come up with the formula? The first thing is you're like, well, is it arithmetic? No. Right, I'm not adding a certain number. Is it geometric? No, I'm not multiplying by a certain thing each time either, right? So I've ruled those out, so I'm like, ah, crap. That means I got to come up with the formula, right? So I always like to, write them out. You're just going to have to inductively reason this. You know, n is 1 here, n is 2 here, n is 3, n is 4, n is 5. So let's just look at the numerator for just a second. What am I doing to the n to get 2? And then what do I do to 2 to get 4? Blank 3. 5. What's that relationship there? 2 to the power n. Yeah, 2 to the power n. So an 2 to the n, that'll spit out my numerator, right? Like 2 to the 5th is 32, 2 to the 4th, and so on, right? See how that spits out our numerator there? And then the denominator is just, the denominator here ends up being 2n minus 1. If you check that, 2 times 1 minus 1 is the 1. 2 times 2 is 4 minus 1 is the 3. 2 times 3 is 6 minus 1 is the 5. 2 times 4 and so on. 2 times 10 minus 1. See, and so, okay, so we got our explicit formula finally. So that's the first part. Now we can, so number 1, find the formula. Number 2, does this thing converge or diverge? Well, let's run the limit as n goes to infinity of 2 to the n over 2n minus 1. And right now it's infinity over infinity, so we're going to have to use L'Hopital's rule again. And so we've got a limit as n goes to infinity of the natural log of 2 to the n over 2 minus 0. And so this ends up being infinity over 2, which is infinity, right? 2 to the n. And so, yeah, this diverges. The sequence just keeps getting bigger and bigger. Just shoots to infinity. Doesn't have a limit. Notice on these, see how the first 3 terms are all the same? Right? Let's say you didn't have the rule. Well, in order to determine the convergence or the divergence, you gotta know their rules. You gotta know the explicit formulas. Otherwise, you just don't have hope. Like this first one, the first one converges to 0. The second one will converge to 0. Third one converges to a 9th, actually. And the last one diverges, right? Would you have known that if you just had the first set of 3 numbers? No, because all the first 3 numbers are all the same, right? There's no way to know that without the formula. So thus the power of the nth term formula. If I'm looking at this one, determine the nth term for this sequence, do you see how, first of all, it's alternating negatives, positives on this? So I'm thinking to myself, well, first of all, it's alternating signs. So an easy way to think about that is it'll either be -1 to the n if it starts out negative, or it'll be -1 to the n plus 1 if it starts out positive. Well, this one starts out negative, right? I'm letting n be 1. So I'm going to use the -1 to the n. That'll be part of my formula here. Okay. Now let's just look at the numerator for a second. Let's just examine. Now that we've accounted for the negative, let's look at the numerator. We've got -2. N is 1, n is 2, n is 3, 4, n is 5. And maybe this one might be a little hard to pick up. Again, I'm ignoring the positives and minuses for a minute. But if I take 3 to the n, like 3 to the 1 is 3, right? 3 squared is 9. 3 to the third, 27. 3 to the fourth, 81, right? You see how that number is just one less than that in the numerator? So my numerator formula will be 3 to the n minus 1. Now again, that's saying I've already accounted for the changing alternating sign, right? I'm ignoring the negative positive for a minute. But that's my numerator. Now I'm looking at my denominator, and I've actually got a factorial. That's 1 factorial, that's 2 factorial, that's 3 factorial, 4 factorial, that's 5 factorial. So the denominator is n factorial. And so if you put this all together, the nth term, there's the alternating sign, and then you've got, here's my numerator, and there's my denominator, okay? So that's your explicit formula. And so then the question becomes, well, what happens? Does this converge or diverge? Well, there's a theorem called the, oh, I didn't put it right there. It's called the absolute value theorem that says if the absolute value converges to 0, then the one with alternating signs, possibly in our case, or in other words, without the absolute value, would also converge to 0. So let's think about this ignoring the alternating signs. So in other words, let's apply this absolute value theorem for a minute. Now, there's no way to apply L'Hopital's. We've got infinity over infinity, but we can't take the derivative of n factorial is the problem. There's no rule for that. And so we're just going to have to examine this inductively for a minute. Does this go to 0? And it actually does go to 0. Why does this go to 0? That's because this gets way larger, substantially larger than the numerator. The larger you get, the bigger the gap gets, if that makes sense. You could throw in like n being 50, and you'd probably see like a 20 or 30 digit difference between the two, the numerator and the denominator, with the denominator being much bigger, right? And so this is kind of a table of values situation with no other options there. Well, two concepts that play a role in determining convergence, divergence, is monotonic sequences. And with monotonic sequences, you have two types. Either your terms are, if you ignore the or equal to part, this is like increasing, but we're going to call that non-decreasing, because they could be the same every time. They could be the same. Likely they're increasing the whole time, but if see that or equal to part, right? It could be the same thing. So non-decreasing is an example of a monotonic sequence, or non-increasing. In other words, they're decreasing throughout the sequence, term to term, or they're the same. Those are both examples of monotonic sequences. Let's determine whether it's monotonic or not. This one was the old 2-4-2-4 one, right? Well, is it increasing the whole time? No. Is it decreasing the whole time? Is it the same number every time? No, so it's not monotonic, right? It's alternating. Not monotonic. All right, how about this one? If we were putting terms in, you'd have 1, you'd have 4/3, you'd have 6/4, you'd have 8/5, you'd have 10/6, you'd have 12/7, and so on, right? In other words, 1, 1.3, 1.5, 1.6, 1.6 repeated, 1.714, so on. Does it increase? Does it continue to increase? Yeah. So we say yes, it's monotonic, and we'll be technically proper. This is non-decreasing. Because remember, it could be the or equal to, right? You'd have 1, then you'd have 2 squared over 2 to the 2 minus 1, so you'd have 4/3, you have 9/7, 16/15, and so on, right? So you got 1, 286, and you have 1.06, and so on. So you can see how it goes up and then it comes back down, right? In other words, the second term, this is not monotonic, right? It's not strictly increasing or strictly decreasing or strictly the same, right? So we're not monotonic. Because this term, right, it's going up to 1.3, but then it goes down, right? You either got to keep going up, keep increasing, or you got to have them all decrease, or you got to have them all the same. Well, let's determine if these are monotonic or not. 1, 2, 3. Can you see how that just keeps getting bigger, bigger, bigger? So we say, sure, that's monotonic. It's increasing, or we'll use the proper term, it's non-decreasing. Second one, 1/2, 2/3, so 0.5, 0.6, 0.75, right? Also increasing. Next one. It is monotonic. See how it's decreasing the whole time. In other words, non-increasing. The next one. Yeah. You can say either one is the same, right? It's the or equal to situation. So in other words, it's both non-increasing and non-decreasing. It's fitting both of those definitions, right? And then the last one? Good, alternating. All right, well, a bounded sequence, we could be bounded above, we have an upper bound, or we could be bounded below, or maybe we're bounded above and below type of deal, but it's a sequence is bounded when it's bounded above and it's bounded below. So like if you look here, this is a monotonic sequence. See how it keeps increasing the values, and then it's limiting, it's converging to whatever this L value is. It's converging to that number as it gets closer and closer and closer to it, right? It's bounded below by whatever that is. Looks like it's 1. And it's bounded above by L. Okay, so a lower bound and an upper bound. And let's talk through a few of these here. A to the n is 1 over n. Let's think about 1 over n for a minute. If we were listing those, we'd have 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on. Right? And so we have the upper bound. See how it's decreasing in value the whole time? Right? So if you're making a few notes on this. The upper bound is 1. That's the highest value it has, right? And then it just goes down, down, down until it approaches your lower bound. What's your lower bound here? 0, yeah. This is going to 0, right? So the lower bound is 0. And this is monotonic, right? It's non-increasing. Non-increasing, this is monotonic. Therefore, this is, since it's bounded and monotonic, it must converge. And of course it converges. We know it converges to 0. All right, let's look at this next one here. B to the n, n squared over n plus 1. If I was listing those, 1 squared over 1 plus 1, 1/2, 4/3, and 4, 16, 25 or 6, so on. And can you see how this is increasing, getting larger, larger, larger? So this is also monotonic. In other words, non-decreasing. And it's increasing, so I do have a lower bound. So I'm bounded below by that lowest term, that 1/2. Is there an upper bound? Yeah, because no upper bound. As it just shoots to infinity, it just keeps getting bigger, 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 right? So therefore it's divergent. It diverges. -1 to the n. -1 to the 1, -1 squared, -1 to the 3rd, -1 to the 4th. It's not monotonic, right? Because it's alternating. The upper bound is 1, the lower bound is -1, so it is bounded above by 1 and below by -1. But it's still divergent, right? It's not monotonic. It's a problem. Good problems for U-triad problems. Determine whether the sequence is bounded. Again, to be bounded, it's got to be bounded above and below, right? So if you're looking at this 1, 2, 3, dot, 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 notice it just keeps getting larger. So there's no upper bound. Is there a lower bound? Yeah. 1 is the lower bound. We could call that the greatest lower bound, if you will. Is that some term? Bound. So yeah, overall not bounded. Got to be bounded above and below. This next one. 1/2, 2/3, so 0.5, 0.6 repeated, 0.75, dot, 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 dot. See how it increases? So this is bounded below by 1/2. That's the lowest term. In other words, the greatest lower bound. It's lower bound. What is it bounded above by? Yeah. Let's look at that. We have the explicit formula, n over n plus 1. Infinity over infinity, L'Hopital's rule. Or we can do this algebraically. Let's practice the little algebra on this. Take that n, divide everybody, multiply the bottom by 1 over n and the top by 1 over n. So this is the limit as n goes to infinity of 1 over 1 plus 1 over n. This goes to 0, so I got 1 over 1 plus 0 is just 1 over 1, right? You could have also thought this in terms of pre-calc. When the degree of the numerator is the same as the degree of the denominator, then you take the leading coefficients. It'll approach that, right? That was the horizontal asymptote stuff, right? If the degree of the numerator is less than the degree of the denominator, it'll approach 0. Again, these are for polynomials, right? And the degree of the numerator is greater than the degree of the denominator, then it shot to infinity, negative infinity, again, for polynomials. So again, this is bounded below by a half, bounded above by 1. So yeah, this is bounded because it's got both bounds. Thanks so much for watching. See you next time.